Alright, so this week I have section 3 of chapter 7, which is pages 166 to 170. This section starts off talking about assumptions and linearity. So, in this we learn that the use of the regression equation requires that the underlying relationship is linear, or else it won't make sense. And that's where homoscedasticity comes into play. I hope I said that right. So the use of standard error of estimate, which is y/x, assumes that, except for chance, the dots of the original scatter plot will be dispersed equally about all segments of the regression line. You need to worry about violating this assumption only when the scatter plot reveals a dramatically different type of dot cluster, when the dots lack equal variability about all line segments as shown below. And then we move on to the interpretation of R squared. So this provides a key interpretation of the correlation coefficient, but also a measure of predictive accuracy that supplements this x, y/x value. Repetitive prediction of the mean. So if you only know one set of scores, for example, if you only know y and you don't know x, it's possible to always predict the mean for each score, and this applies a frame of reference against which to evaluate customary predictive effort based on correlation between variables. Predictive errors, so you can compare that repetitive prediction of the mean to y values, y prime values, so finding predictions based on the least squares equation. So will produce a lower margin of error is what we get out of this. So if you're between using the repetitive predictions or the least squares equation, you want to use the least squares equation because it will give you a lower margin of error, predictive error. And here's just showing you the difference. Okay, so it talks about error variability and the sums of squares. So in order to more precisely evaluate the accuracy of predictive efforts, measurement of the collective errors produced by each effort are needed. So the sum of squares of any set of deviation errors can be calculated by first squaring each error and then summing all the squared errors. So then we come up with the equation SS subscript y equals the sum of y minus the mean of y squared. And then we get into the proportion of predicted variability. So SS subscript y measures the total variability of the y scores that occurs after only primitive predictions based on y mean are made. And then SS subscript x/y measures the residual variability of y scores that remains after customized least square predictions are made. So in order to obtain an SS measure of the actual gain in accuracy due to the least square predictions, you have to subtract the residual variability from the total variability. So you would do SSY minus SSX/y/x. And then in order to express this resulting difference as a gain of accuracy relative to the original error variability for the repetitive prediction of y mean, divide the difference obtained by the previous SSY. So that would leave you with SSY minus SS subscript y/x divided by SSY. And then this result represents the proportion or percent gain in predictive accuracy when the repetitive prediction of y mean is replaced by a series of customized y mean predictions based on least squared equation. And then when squared, the R value equals the proportion of predictable variability. And then we go into the squared correlation coefficient, which is R squared, which is the proportion of total variability in one variable that is predictable from its relationship with the other variable. And this is the interpretation they give you. But the equation that you would use to find this would be SSY equals summation of y prime minus y mean squared.